Good morning, guys. Okay, so we're gonna finish the third chapter. There is just one exercise left from the third chapter, and this is the U-Walker equation, right? Maybe you remember. I was mentioning that. So for a stationary autoregressive process regarding the correlation. Okay. Now let's go basically back to the exercise 3.6. Okay. So apologize for that. And this was about the autoregressive. Okay, so this is exercise 3.6, and we had an autoregressive process here. So y is an autoregressive process of order 2, and so therefore, I mean, yt is basically equal to, and you said this was the constant plus a1 times yt minus 1 plus a2 times yt minus 2, okay, plus the noise, okay. Or basically, if you write this in terms of the lag polynomial is, I mean, the lag polynomial times y is the constant plus the noise, and so basically the lag polynomial equals 1 minus a1 times L minus a2 times L squared. That's the representation that we get here. Okay. Now we supposed to, I mean, here in part C, this is what we're supposed to do. We're supposed to calculate the correlation coefficient. Okay, so for the correlation coefficient for leg 1 with respect to leg 1, and the correlation coefficient with respect to leg 2 using the U-Walker equation. And of course, if let's say, so this is what we're looking for, and basically the equation that we have here is that the correlation at point H is equal to A1 times the correlation at point H minus 1 plus the correlation of the process with respect to A2 times that. Okay, so A2, this is the coefficient. Okay, so A2 times the correlation of that for at point H minus 2. Okay, so this is what we're supposed to do here. Okay, so these are the U-Walker equation, or this is the U-Walker equation. Okay. And the thing is this, I mean, we have to do this. Now let's start at, and we do, okay, so suppose we have that H is equal to 1. Now if H is equal to 1, then the U-Walker equation becomes as follows. So here you have the correlation, or the autocorrelation of the process, to be precise, at point 1. Okay, so because H is equal to 1, so here you have A1 times the autocorrelation at point 0, because if H is equal to 1, then you have 1 minus 1, which is equal to 0, of course, and A2 times the autocorrelation at point minus 1. Okay, so this is what the equation becomes. Now, basically what you have here is that, I'm using a different color. So basically what you have here is that the autocorrelation at point 0 is equal to 1, of course. Okay, because this means that the variable, this refers to the correlation of the variable with itself. Okay, and this is always equal to 1 because the linear relationship of a variable to itself is always equal to 1. And we have, and maybe you remember this statement. So here you have the correlation with respect to H is going to be equal to the correlation of the point with respect to negative H. Okay, so because this is symmetrical. Okay, so the correlation of between time t and t plus H is going to be the same thing as t and t minus H. This is what we have already shown. Okay, so basically these two, this one and this one, are equal. Okay, that's obvious, and this is equal to 1. So if you plug everything into that, okay, so then basically what you have is that the correlation at point 1 is equal to A1 plus A2 times the correlation at point 1, of course, right? Because this is these two are equal. Okay, and now you solve this for the correlation. That's it. Okay, so if you solve this for the correlation, basically what you're gonna get. Okay, so if you put that here to the right hand side of the equation, and then you just factorize it. Okay, so then you factorize this. Okay, and then you divide by the remaining factors. So here you have the correlation equal 1 times 1 minus a2 is going to be equal to a1. So hence the correlation is of course equal to a1 divided by 1 minus a2. Okay, that's the first correlation. Okay, so this is how you would basically calculate the correlation, the autocorrelation here for the process of t and t plus 1 basically. Okay. Now, okay, so then we can go on basically. So if let's say age is equal to 2, okay, because that's going to be the next thing. So if age is equal to 2, then basically what you're going to get is from this equation, okay, so from the Walker equation, so you put 2 in there, okay, so the autocorrelation, okay, of the process at point 2 is going to be equal to a1 times the autocorrelation at point 1, obviously, okay, so here you have h minus 1, and if h is equal to 2, then you have 1, of course, and here you're going to have 0, right? So this is going to be a2 times the autocorrelation at point 0, which is basically the autocorrelation where you have that this is equal to a1, this is equal to 1, and this is equal to what we had here. This was 1 over 1 minus a2, right? So no, sorry, a1 over 1 minus a2. So this becomes, obviously what you have here is that a1 squared over 1 minus a2 and then plus a2. That's going to be it. Okay, so this is going to be the second autocorrelation. And you could go on and on and on and on for that. Okay, so I mean you could continue, right? So basically, I mean you could do also the autocorrelation at point 3. That's quite obvious. Okay. Is that clear, guys? Okay, so far? Now let's prove the equations. Okay, so basically you could go on. And now we're supposed to prove the equations. Okay, so I'm talking about this Walker issue here. Okay, so this is part of the exercise 3.5 as well. Okay, so this is the last part. Okay, so in the first part of that exercise, okay, so we have exercise 3.5. Okay, so basically what we have here is that if, let's say, y is an autoregressive process of order p and stationary, okay, then first off we have that the covariance, okay, so the covariance of yt and yt plus h is going to be equal to a1 times the covariance of yt plus 1 and yt plus h, sorry, yt and yt plus 1 minus h. Okay, I made a mistake here. This is not the correlation that we were talking about. So yt and yt plus h minus 1, that's the first one. Okay, so this is the same here, as you can see. For the autocorrelation and the autocovariance, we have the same. Okay, so you have h minus 1, so that's a time lag that you have here. Okay, so then you have a2 times the autocovariance of yt and yt plus h minus 2, and so forth. And the last one is going to be ap times the autocovariance of the process yt and yt plus h minus p. So this is how it evolves. Okay, so if you have 1 here, then you have 1 here in the index, 2 here, 2 here in the index, P. That's how it evolves. P here for the index. Okay? And the errors, of course, fall out. Okay? And based on that, you can basically you can do this with the correlation itself. Because if you divide the covariance by the variance of the process is stationary, so it doesn't depend on time. Okay, and for the variance there is no time lag actually. So if you divide this by the variance, then basically you get the same thing for the correlation too. Okay. Remember, the correlation is equal to the covariance divided by the product of the standard deviations. But the standard deviations are equal because the process is stationary. So since the process is stationary, then you have the standard deviation times the standard deviation is equal to the variance, okay, in the denominator. So you have the covariance divided by the variance will be equal to the correlation of the process. Okay. Now, so that's why it's enough to show this. Now, how would you do this? Now, first off, of course, I mean, basically you can assume that yt. Okay, so this is how the process is. Okay, so yt is an autoregressive process. So basically, it looks like this. So you have a1 times yt, a1 times yt minus 1 plus a2 times yt minus 2 plus etc. plus ap times yt minus p plus the plus the noise. Okay, and based on that, you can also obtain yt plus h. So yt plus h is just you would add here plus h here for the index. So this is going to be a1 times yt plus h minus 1 plus a2 times yt plus h minus 2, etc., plus ap times yt plus h minus p, and then plus the noise. Epsilon t plus h, of course. Okay, so because we have the time index t plus h here. Okay, so this is t plus h, what you have. Okay, and here above you have just t. Okay, this is just what you replace. Okay, that's relatively easy to understand. Okay, now so there you can compare the two processes to each other. Now, of course, there is another representation for the process yt, and this is what you basically know about it because the process is stationary. Okay, so yt is basically, I mean, you have had this, the expectation is 0. So here you have, it can be written as the following sum. This is what we have also considered already. So the sum of some coefficients, okay, times epsilon t minus h here. Okay, so the h goes from 0 till plus infinity. So this is what you would get from the process. Okay. Now this is important to keep that in mind because you would see how the covariance is. Okay, so here in this case the expectation, okay, so if you see this, the expectation of the process, as you see, is of course equal to 0. Okay, so the expectation of the process is equal to the expectation of the sum. The expectation of the sum is the sum of the expectations, right? And so you have the expectation of a linear transformation, the white noise, which will be equal to 0, of course. Okay, because the expectation of the white noise is equal to 0. Okay, so that's quite obvious. So that the expectation of the process is 0. So if you want to calculate the covariance of the process, okay, then basically it's enough to compute the expectation of the product of yt and yt plus h, okay? Because the covariance is of course equal to the expectation of the products minus the product of the expectations, right? Remember that. So the expectation of the products minus the product of the expectations. Okay, so this is what I'm talking about. So the covariance of two random variables is equal to the expectation of their products minus the product of the expectations. But if the expectations are both 0, which is the case here for no matter what, okay, process is stationary and 0 doesn't depend on time here. So then the covariance becomes the expectation of the products of the two. That's going to be it. Okay, so this is just an explanation for this. Okay, now what I'm doing here in a second step is I'm replacing basically so you have it here yt plus h by this expression here. Okay, so here you have yt plus h. Okay, so this is what I'm doing. So basically you have the expectation of yt, and then what I'm going to do here is I'm going to put in yt plus h here into this equation, right? So that's what I'm going to do. So here you see yt plus h here above, so this is what I'm doing. Okay, so I replace that with, so here you have a1, okay, times yt plus h minus 1, blah, 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 right? So plus a2 times yt plus h minus 2, and so forth. And then I have the last one, okay, so then you have ap times yt plus h minus p, and then you have the noise too, okay, so epsilon t, and then close the parentheses. This is what you would have, okay, so if you replaced yt plus h by this expression, okay. Now here, of course, the expectation of the sum will be equal to the sum of the expectations, yes?
Is it the y equals t plus
t plus h, yes, sorry, I forgot that. That's correct, so t plus y, t plus, epsilon t plus h. Okay, so the noise, this is what you have as an index for the noise, okay? Thanks. So basically the expectation here of the sum is the sum of the expectations, right? So here you have the expectation of, and then you have it here, so I'm gonna write this as follows. So here you have a1 times yt times yt plus h minus 1, that's the first thing, okay? So then plus the second expectation, so the expectation of a2 times yt plus h minus 2, okay? And then the last one, okay, so the last one here from the process is ap times yt plus h minus p, okay? And then you have the expectation of yt times epsilon t plus h, okay, so for the noise too. Now here you have basically that this is equal to 0, because the future realizations of the white noise doesn't correlate with the past of the process, okay? It should be the other way around, basically. Okay, so the process correlates basically with the past of the white noise, let's say. Okay, so but not if you look at it forward. So the realization, because h is strictly greater than 0, right? So since h is strictly greater than 0, this expression, okay, so here, I mean the expectation, okay, so the expectation of that expression is obviously 0, right? So here you have that this is just going to be the sum of these expectations. And if you take the a1 out, okay, so here you have a1 times the expectation of the product of the two random variables, which will equal to the covariance of yt and yt plus h minus 1, obviously. So this is going to be equal to the covariance. And here you have the same thing. So if you take a2 out, so then it's going to be a2 times the expectation of yt and yt plus h minus 2, and so forth. Okay, so and then you have the last expression ap, which is ap times the covariance of yt and yt plus h minus p. This is going to be it. Okay, so that's basically how you would prove it. Okay. Now again, if I said this, but if you divide both sides of the equation by the variance, then you would get, you would get the autocorrelation replaced by the autocovariance replaced by the autocorrelation. Okay. So basically, that's a proof. This is it. All right. That's going to be okay. Now I wanted to tell you something about exercise 3.7. Okay, so exercise 3.7 is about so-called linear processes. Okay, and it's okay. So these are. I'm not going to solve the exercises. It's just for you. Okay, just for practice. Okay, so what is a linear process? Okay. So linear process is basically a process, okay? So that can be written as follows. So here you have a constant, plus, and then you have a sum, which is not finite, and then you have some coefficients times a y noise, okay? And basically this looked like quite similar as the autoregressive processes that we had here, if they were stationary. So the thing is this, and this is the general process here, and what's important here is that any stochastic process which is stationary can be written as a linear process, okay? So this is just a generalization. So any stochastic process, okay, process that is stationary, okay, okay, can be written as a linear process. Okay. So basically, if you just examine the properties of the linear process, and basically you would examine a stochastic process which is stationary in general. Okay, so this is, sorry, this is missing here, obviously. Okay. So that's what, the linear processes are about. Now what you should do is you should compute the expectation of the process, the variance and the covariance. Okay? And basically this is something that we had done in a previous example. So I'm not going to do this here for this process, but you should do that, or you should try that. We did this for the autoregressive process of order P, and the only difference was that we have, instead of C, we had just alpha. Okay, and the constant was B divided by the lag polynomial at point 1. That was just the only difference, okay? But this is just a generalization, so the same properties hold, okay? You can try that. So, but that is important, so any stochastic process that is stationary can be written like that, okay? That's the basic property here. Now, okay, so you should try to solve this exercise by your own. I will, of course, upload the solutions to the exercises as well. Okay, but it takes a little bit more time for me just to edit it. Okay, so you will get the solutions of the exercise later. Okay, now if that is clear, okay, so what basically the most important thing is that the stationarity conditions that we developed for autoregressive processes, okay, both for the first order autoregressive process, which were easy, and basically for high order autoregressive processes as well. In particular, we also examined the second order. Okay, so that is going to be important. Okay, and if you have this, then I'm going to move on with the next chapter. Okay, and the next chapter will be about so-called moving average processes. Okay, so moving average. And okay, so moving average process, and also we're going to do some mixed models as well. Okay, so mixed models, we're going to have this. Okay. So mixed model, an example would be if we put the autoregressive process and the moving average process together. So then you're going to have a autoregressive moving average process, but I will introduce it to that. Okay, now what is the definition? Okay, so the definition is as follows. Okay, so basically a stochastic process Y, okay, is called an autoregressive, or let's say moving average process first. Okay, so the notation here is that. Okay, so MA for moving average process of order Q. Okay. Okay, so this is what it denotes. Okay, so this is the moving average. Okay, so moving average process of order Q. And the moving average process of order Q can be represented as follows. So here you have yt, okay, so this is the process, which should be a moving average process. And basically, you don't have an autoregressive model here. All you have is a constant plus a noise, okay, and plus some coefficients here that you multiply by the lagged values of the noise. So here you have b1 times epsilon t minus 1. Here you have b2 times epsilon t minus 2, and so forth, okay? So bq, okay, that's the last one, times epsilon t minus q. So that's how it evolves, okay? So here you have b1 for the first coefficient, and the white noise at point t minus 1. Here you have b2, okay, as the coefficient times white noise at point t minus 2. And the last one is going to be bq times epsilon t minus q, so the white noise at point q, okay, so the t minus q. So this is going to be a so-called moving average process. So all you have is basically the lag values of the white noise, okay, and that's going to be it. Okay, so now the properties of that process are relatively easy to examine, okay, so I also write this in terms of a sum, okay, so basically what you have is that you have a sum, okay, that goes from g is equal to 1 to q of bj times epsilon t minus j, okay, so this is just a summation index here, so that's how you represent the process, okay. Now in this representation, the properties of the process are relatively easy, relatively simple, let's say. Okay, because what you see immediately is basically that the process is stationary. Okay, so the expectation doesn't depend on time, the variance doesn't depend on time, and the autocovariance doesn't depend on time either. Yes?
If there is not epsilon t in your sum.
Oh yeah, there is one noise missing, yes, you're right. One noise is missing. Thanks. I forgot about it. Yes. Again, just a moment. Okay, sorry about it. So this noise is missing. Yes. That's obvious. Thanks. Okay. Good. Now, okay, so I mean, let's consider an easy example first. Okay, so let's say that basically what you have is is a moving average process, okay, of order 2. Okay. So this is a second order moving average process. Okay. Now if basically y is a moving average process of order 2, then what you have here is that yt equals the constant plus the noise at point t plus b1 at times the noise at point t minus 1 plus b2 times the noise at point t minus 2. Okay, so this is how it evolves, obviously. Now what we're going to do here is, of course, we're going to calculate the expectation of the process. Now the expectation of the process, you can see that you have a sum here. The expectation of the sum is going to be the sum of the expectations, right? Okay, so this is going to be the expectation of a constant, which is going to be the constant itself, plus the expectation of the noise. Okay, I would write it down anyway, so 10 plus b1 times the expectation of the noise, okay, and then plus b2 times the expectation of the noise here. Okay, and now, of course, the expectations of the noises here are going to be 0. So the expectation is going to be just equal to the constant, so that means that the expectation of the process does not depend on time. Basically, I just already announced this is going to be a stationary process, so no matter what you do, this is just going to be it. Okay? Now we're going to calculate the variance. Okay, so the variance of the process as well. That's also relatively easy, because you have the variance of the sum is going to be equal to the sum of the variances, as you might know. Right? So the variance of the sum is going to be equal to the sum of the variance, so you have the variance of the constant. Now the variance of the constant is going to be equal to 0, obviously. Alright? And then you have the variance of the white noise. Okay, so the variance of the white noise is going to be sigma squared, right? So then plus the variance of the linear transformation times the white noise. So if you multiply B1 times the white noise, and when you calculate the variance of it, you're going to get rid of the B1, then you have the square root. So this is going to be B1 squared times the variance of the white noise. Okay, obviously, and then B2 squared similarly, so times the variance of the white noise at point t minus 2. Now, of course, the variances of the noise, okay, are all equal to sigma squared. Okay, so this is a constant, right? So that's always going to be the same, right? That's obvious. So here you have sigma squared plus B1 squared times sigma squared plus B2 squared, okay, times sigma squared. So then you're going to get what you have is that sigma squared times 1 plus B1 squared plus B2 squared, okay, obviously. Right? That's going to be relatively easy. Okay? Now, if you look at the autocovariance, okay, so yt and yt plus h, okay, so the autocovariance, there are two cases we need to consider. Okay? Now, the first case is going to be, and this is what you need to generalize. The first case, okay, is going to be that h is going to be greater than 2. Because if h is greater than 2, then we have something quite interesting here. Okay? So if h is greater than 2, I mean, since this is what you have for the expectation, right? So if h is greater than 2, then what you have is basically you're going to get the covariance, and all I'm doing is just to plug it in the process. So here you have B1, okay, white noise, so the constant plus the white noise, okay, plus B1 times epsilon t minus 1 plus B2 times epsilon t minus 2, okay, so that's going to be the first expression, and the second expression is going to be the constant plus the white noise at point t plus h plus B1 times the white noise at point t plus h minus 1 plus B2 times epsilon t plus h minus 2. That's going to be it. Okay? So h is greater than 2. Now, if h is greater than 2, then what you see here is that the noises do not overlap anywhere. Okay? So, I mean, let's say the greatest time lag here for this expression, okay, is the time t plus the t, right? Okay, so that's the greatest one. And the smallest one is here is going to be epsilon t minus 2. Okay, so t minus 2 is going to be the smallest time lag, and for this you're going to have t. Okay. So basically, if you look at the timeline, okay. So let's, if you compare this case to it, so let's say we have t here. So this is where you have t. Okay, let's see, we'll move a little bit forward. Okay, and t, and here you have t minus 2. Okay, so this is the time range that is covered basically by the process. Okay, by the first one, obviously. Okay, and what about the other one? Okay, the other one is you have t plus h, right? And t plus h minus 2. And suppose that this is going to be here. So here you have, let's say here you have t plus h, okay? That is a time lag which is a little bit to the right, okay? So here, if you have the time here, okay? So here you have t plus h, and t plus h minus 2 is, let's say, it's here, okay? So t plus h minus 2. And now here in this diagram, you can clearly see that if age is strictly greater than 2, okay, which is supposed to be the case here. So if age is strictly greater than 2, then the white noises do not overlap, okay? So if they don't overlap, then the correlation is what? The correlation is, of course, 0, obviously, right? Okay, so if they do not overlap here, okay, so this is going to be, maybe I just put more emphasis here on a little bit more properly here. So this is the upper bound and this is the lower bound here. That's what you're going to have here and here, okay? So if age is greater than 2, then of course the time lapse do not overlap, of course, okay? So the time length do not overlap, so the process is not autocorrelated. So in this case, the autocovariance is going to be equal 0, obviously. Okay. So that's going to be the result. Okay. So if age is greater than 2, then the autocovariance is going to be greater than 0. Okay. Right. Okay. Now, what about, let's say, for instance, if okay, so in case, let's say, age is less than or equal to 2. Okay, so if this is less than or equal to 2. Okay, now look at the covariance again. So the covariance of yt and yt plus h, all right, is going to be equal to, and this is what you have for the process. Okay, so no big deal about it. Okay, so what you have is the covariance, okay, of the constant, okay, plus the first noise, okay, plus B1 times the second and plus B2 times the third. Okay, so that's going to be the first expression. And the second expression is going to be, in the case of here, that's the second variable. So here you have the constant plus the noise. Okay, so plus B1 times epsilon t plus h minus 1 plus B2 times epsilon t minus h, epsilon t plus h minus 2. That's going to be the last one. Okay, so you have epsilon t plus h minus 2. Okay. I'm not sure whether or not this is clear. Okay, but basically it's supposed to. Okay. All right. Okay. Now the question is, in which autocovariants do overlap? Okay, so here you have basically that h is going to be equal either to 2 or to 1. Okay. All right. So h is going to be either equal to 2 or to 1. Now the question is which of the autocovariants is going to overlap if, let's say, h is equal to 2. Now if h is equal to 2, then what you have here is that you have epsilon t plus 2, then you have epsilon t plus 2 minus 1, which is going to be equal to epsilon t plus 1. All right, and epsilon t is going to be the last one. Okay, so this will, if let's say h is, okay, so if h is equal to 2, okay, then this thing will become epsilon t plus h minus 2, which is basically epsilon t, right? So this epsilon t will overlap with this one, and all others cancel out. Okay, you understand? So all others cancel out. So these will be the only two that are going to overlap here. Okay, so this one and this one. Okay, if let's say h is going to be equal to 2. Okay, if h is going to be equal to 2, then these are the only that overlap. Okay, so then of course you have the covariance of that 2, which is going to be equal to b times the variance because they are equal. Okay, so this is going to be, in that case, this is going to be equal to the variance of the white noise times B2, which is going to be equal to B2, okay, times the variance of the white noise, which is going to be sigma squared, obviously. Okay, you see? So because these are the two that are overlapping. Is that clear? Okay. Now, and the others don't, so you have t plus 2 here, so you have t plus 1, okay, and these are nowhere to find here. Now what about, let's say for instance, if, and what you would get is that basically, what about, let's say if, let's say age is equal to 1. If age is equal to 1, then you have t plus 1 here, no overlap here with that process. So you have t plus 1 minus 1, which is going to be equal to t. Okay, so this will overlap, okay, this process will overlap with that one, okay, and then here you have epsilon t plus 1 minus 2, so epsilon t plus 1 minus 2 is going to be equal to epsilon t minus 1, okay, so epsilon t minus 1 will overlap, okay, so this process will then overlap with that one, you see? Okay, so these are the two, I mean, the gray ones are going to overlap, and the orange ones are going to overlap if age is going to be equal to 1. You understand this? Okay? Now, of course, I can use that, so the covariance of that 2 is going to be equal to B1 times the variance of the white noise at point T. And the variance of the white noise at point T is going to be equal to B1, of course. Okay, so this is going to be, that's what you have here, so this is going to be B1. Okay, so times sigma squared. Okay, so that's what you would have here for the white noise. Okay, and here you have the other two, so B1 times B2 times sigma squared, so that's going to be the second part. Okay, so B1 times B2 times sigma squared. And the others just cancel out, okay, because they don't overlap. And that is something you have to consider also. Okay, so that's what you have to consider also. Okay? Right? Okay? And of course, and this can be of course generalized, so this is going to be the covariance here of the two. Now this thing can be generalized, and I did this in the exercise, and hopefully you can do that too. Okay, so I will, you can practice that, so I will generalize that result by the following lemma. Okay, so here you have the following lemma. Okay. So basically it says that if you have a moving average process of order Q, then what you have is basically that of course then the process is stationary. Okay, so then Y is stationary, obviously. And we have the following properties. Now the expectation is, of course, of the process is going to be equal to the constant, okay? And the variance, okay? So look at the variance of the process. Now the variance of the process, as you see, and this is what you're going to get here from it. Okay, so that was the variance. So here you have sigma squared times 1 plus B1 squared plus B2 squared. Now if you generalize that for instance the third order autoregressive process, then you have B3 squared and so forth. Okay, so if you want to generalize that, so you're going to get, for the variance, you will get sigma squared times 1 plus B1 squared plus B2 squared plus blah 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 plus BQ squared. Okay? And the covariance, okay? So the covariance of the process, if you want to generalize that, okay, so will consist of basically two things. Okay, so the covariance will have two cases. The covariance will be equal to 0, okay, if the lag here for the covariance is greater than the order of the process. So here you have, if let's say the lag was greater than 2, then the autocovariance was equal to 0. Now in the general case, if the lag is greater than the order of the process, then the autocovariance is going to be equal to 0. So in that case, it's going to be 0 if the lag is greater than the order of the process. Okay? So that's because the autocovariance will fall out. And in case the lag is less than or equal to the order of the process, you will have the following expression, and this is what you can do to generalize the process. Okay, so here you're going to do is you have 1 times BH, okay, plus B1, so you can call this B0 times B1 plus H, okay, and this goes on. Okay, so then you have plus B2 times B2 plus H, okay, and so forth. And the last one is going to be BQ minus H times BQ, okay? So that's going to be it, okay? And times sigma squared. And that is relatively similar to the autocovariance here. If you just take that, for instance, to be equal to B0. So if you introduce B0, then you would get the same thing. Okay, so that's what you would get if you would generalize the case. Okay? But you don't need to verify that. I will do this in the exercise, so then you're going to see that this is going to be the generalization of the autocovariance. Okay. Now this basically means that the memory is finite. Okay. So if the time lag is of the autocovariance is larger than p, okay, so then the autocovariance is going to be equal to 0. So that means that the memory of the process is finite. Okay. There is no autocorrelation for lags that are greater than the order of the process. Okay, so that is interpretation of a finite memory. Okay, so this is what I will add here. So this is the interpretation of finite memory. Okay, no autocorrelation whatsoever. Okay, if the time lag for the autocorrelation is too large. Okay, meaning that larger than the order of the process. Okay, so the memory is finite. Okay, this was not the case for the autoregressive processes. Okay, of course, where basically you have the autocovariance will approach 0. Okay, but this is just a general case, so that's not what we got here. Okay, so this is a basic property. It's called finite memory. Okay, no autocorrelation whatsoever after a time lag which is greater than the order of the process. Okay, so there's just basically a window. Okay, so let's say evolving window of the process that moves forward. Okay, but it doesn't consider realizations of the past that are too far away. Okay, guys. Now I will continue with the properties. Okay, so we're not going to discuss that. Maybe we can look at an easy example. So an example for B. Okay, so for instance, a moving average process of order 1. So the first order moving average process. Okay. So we're going to see this, and the expectation is, of course, is going to be equal to. This is what you have. It's going to be equal to the constant. Okay. I mean, basically, the moving average process is of course as follows. So here, yt is equal to the constant plus the white noise at point t, okay, plus b times the white noise at point t minus 1. I'm not sure whether or not you see this. I will make that a bit clearer. So here you have yt, and then you have the constant plus the white noise plus the slope. Okay, so b times epsilon t minus 1. Okay, now here you have that the expectation is of course equal to the constant. Okay, because the expectations of the white noises are going to be equal to 0. So the variance of the process is going to be equal to, and this is going to be here, what you see is the variance of a sum is going to be the sum of the variances. Okay, so here you have that this is the sum, the sum of the constant, or the variance of the constant is going to be equal to 0. The variance of the white noise is going to be equal to sigma squared, and b times the variance of the white noise is going to be equal to b squared times the variance of the white noise. So this is going to be equal to 1 plus b squared times sigma squared for the variance of the white noise. Okay, and now the autocovariance. Okay, so basically what you have is the order if the lag coordinate is greater than 1, then what you have is that the autocovariance of the process is going to be equal to 0, obviously, because the processes or the time lags here do not overlap, okay? And if the autocovariance is going to be equal to less than or equal to 1, which means that the autocovariance, the time lag, is going to be equal to 1 here in this case. So it's going to be equal to 1, not just less than 1, but equal to 1, okay? Because the time lag cannot be 0. So then basically what you have is that the autocovariance of yt and yt plus 1 is going to be equal to basically the expectation, okay? So the expectation, what you have is, or let's say the autocovariance, okay? So we can do with the covariance still of the noise, okay? So the constant plus the noise plus b times epsilon t minus 1, that's going to be the first one, and the other one, the other expression is going to be equal to the constant plus epsilon t plus 1 plus b times epsilon t plus 1 minus 1, which is going to be equal to b times epsilon t. Okay, now only, okay, so the constant cancel out, the covariance is not depending on certain constant, and the only noises that do overlap here are going to be equal to epsilon t and b times epsilon t. Okay, so this is going to be equal to the covariance of epsilon t and b times epsilon t, and then that's going to be it. So basically you don't have anything else, right? That's what it left, because all others do not overlap. Okay, so this is going to be the covariance of that expression, and that's basically the b times the variance of the white noise, which is going to be sigma squared. So this is going to be equal to b times sigma squared. Okay. That's the only thing that remains. Okay, obviously. So then, of course, the autocorrelation of the process, I mean, this is stationary, okay, so the process is stationary, so then the autocorrelation of the process only depends on the time lag, and here we have two cases, okay? So if the time lag is greater than 1, then of course the autocorrelation is going to be 0. And if the time lag is equal to 1, then the autocorrelation is going to be equal to the autocovariance divided by the variance of the process. Okay, so the autocovariance of the process divided by the variance of the process. Okay, so the autocovariance was b times sigma squared, and the variance was equal to 1 plus b squared times sigma squared, and you will have that, of course, the sigma squared falls out, so basically you have b over 1 plus b squared for the autocorrelation. Okay, so these are the basic properties here for that case.